Welcome back to Cosmic Galaxy. In this video, we're discussing how much of the universe is dark matter. Make sure to like this video, subscribe to the channel, and hit the bell icon. The majority of matter in the universe is invisible, but its influence on the large structures in space is. Astronomers estimate that dark matter accounts for roughly 85% of all matter in the universe, leaving only 15% for normal matter. According to CERN, dark matter accounts for roughly 27% of all mass energy in the universe, after accounting for dark energy, the name astronomers give to the accelerated expansion of the universe, the European Organization for Nuclear Research. Astronomers have a number of tools at their disposal to calculate the total amount of matter in the universe and compare it to the amount of normal, also known as baryonic matter. The most basic method is to compare the two measurements. The first measurement is the total amount of light emitted by a large structure, such as a galaxy, which astronomers can use to calculate the mass of that object. The estimated amount of gravity required to hold large structures together is the second measurement. When astronomers compare these measurements on galaxies and clusters all over the universe, they find the same thing. There isn't enough normal light-emitting matter to account for the amount of gravitational force required to keep those objects together. As a result, there must be some type of matter that does not emit light, dark matter. The proportion of dark matter to normal matter varies between galaxies. Some galaxies have almost no dark matter, while others have almost no normal matter. However, each measurement yields the same average result. Approximately 85% of the matter in the universe neither emits nor interacts with light. Not enough baryons. Astronomers can validate this result in a variety of ways. A massive object, such as a galaxy cluster, will warp spacetime around it, bending the path of any light passing through it, an effect known as gravitational lensing. Astronomers can then compare the amount of mass seen from light-emitting objects to the mass required to account for lensing, proving that extra mass is present somewhere. Computer simulations can also be used by astronomers to study the growth of large structures. Our universe was much smaller billions of years ago than it is today. Stars and galaxies took time to evolve, and if the universe had to rely solely on normal, visible matter, we would not see any galaxies today. According to cosmologist Joel Primack's lecture, the growth of galaxies required dark matter pools for normal matter to collect in. Finally, cosmologists can go back in time to when the universe was only a dozen minutes old and the first protons and neutrons formed. Cosmologists can estimate how much hydrogen and helium were produced during that time period, using our understanding of nuclear physics. These calculations accurately predict the hydrogen to helium ratio in the modern universe. According to astrophysicist Ned Wright, they also predict an absolute limit to the amount of baryonic matter in the universe, and those numbers agree with observations of modern galaxies and clusters. Alternatives to dark matter. Dark matter could also be a misunderstanding of our gravity theories, which are based on Newton's laws and Einstein's general relativity. Astronomers can tweak those theories to explain dark matter in specific contexts, such as the motions of stars within galaxies. Alternatives to gravity, however, have not been able to explain all of the observations of dark matter across the universe. All evidence points to dark matter being a previously unknown type of particle. It has no interaction with light or ordinary matter and communicates only through gravity. In fact, astronomers believe that trillions upon trillions of dark matter particles are currently coursing through you. Scientists hope to discover the identity of this enigmatic component of the universe soon. Thank you for watching the video.